so today we're going to talk about, so section 3? Yeah. Yes. The section 3, I'm going to talk about writing sets, okay? So from our last video, you saw I wrote the rationals in that crazy way. A natural question we would have, is there an easier way to write it? A more clear way? Writing Q with a line through it is a pretty easy way, but you know what I'm talking about. Well, thankfully the answer is yes. So here's another way that we can write it, and then I will break it down for you. So I'm writing the beginning bracket of a set. So now I'm going to say X, an element in the reals, such that X equals A over B for some A and B that are integers, such that B is not equal to 0. If B is 0, then that breaks everything. Fantastic. So what this part says here, this is where we can grab our elements from. So that's the first section, the section before the line that says the such that. So that's what this stands for. This line stands for such that. Okay, I'll show you there's another way we can write it, colon. Spoiler alert. And then this section, so the section after the line, is all of the restrictions. Okay, so we can't just grab any X from the real line. It has to be an X such that we can write it as a fraction of A over B for some A and B in the integers, such that B is not 0. It also doesn't matter what variable we choose. So we could say Q in R, and then here I'm going to use the colon. So this still means such that. Both of them are the same. They both mean such that. Just whatever one you're feeling like at the moment. Such that Q equals, and maybe let's say X over Y. So that's another way to write it. So another way we could write it is we could instead say what an element's going to look like. So I could start by saying our element can be A over B such that, so now I need to talk about who A and B are, okay? Such that A and B are integers, B not equal to 0. Yeah, so these are 3 different ways to write the same set. Okay, so here are the sets that I would like you to write in the way that we did before. Remember, there's multiple right answers to all of these. So natural numbers, I could say, okay, let's spice it up maybe. How about X in the integers such that X is greater than 0. That works. Even integers, 2X such that X is in the integers. Yeah, that's 1. That works. Kind of the pattern I was hoping you would see is, if you remember, 3 to the 0th power is 1. So what I'm doing here is I have 3 to the, let's say, L. And then I'm going to do my colon for such that L is in the integers. Okay, because I'm able to range over all the integers here. I've got the negatives, the positives, 0, we're all set. Welcome to section 4, Intro to Set Operations. All right, so definitions. So DEFNS is my shorthand for definitions. So first I'm going to start by assuming for all the following definitions, assume A and B are both sets within the universal set U. Then we have the following definitions. So universal set, all that really means is A and B are both contained in it. So let's say A and B are both intervals on the real line, and then maybe use the real line. Okay, all it means is that U contains A and B. The union of A and B is a set containing all the elements of A and all the elements of B. Okay, so it's like if we use that bowl analogy, let's say that this is the set A and this is the set B, and we have the 2 bowls. I have a bigger bowl in the bottom, and I'm just going to dump them both in. But remember, it doesn't matter if elements repeat. That's still the same set. So we're just going to dump both our bowls in. And so this big bowl that we dumped them both in, that's our union. Okay, so this is written. The bowl analogy actually works very well with this one because you could think of the union as the bowl, like this thing, as the bowl that you're dumping them both into. So hopefully that helps. So our second one, the intersection of A and B is a set containing only elements that are in A and B. So this is written A, and then that thing like an upside down union. So how I think about this one is I think of like pins or staples. If you want to pin two pieces of paper together so you only have one little pokey, right? And you want to do it for two papers, you have to let the papers overlap, right? And you have to pin it somewhere where they overlap. Maybe that helps. And the cup thing looks like it's, or cap, it looks like it's stabbing into the paper or something. I don't know. Figure out what works for you to remember it and ride with it. By the end of this course, it'll feel like second nature. 3. The set difference of A and B is the set of all elements in A that are not in B. So this is written A / B. So X such that X is in A and X not in B. Last but not least, the complement of A is the set of all elements in U that are not in A. Okay, so this is written A and then a little C. If we write it as a set like we learned before, we get is the set of elements X such that X is in U and X is not in A. Those are all the new definitions I want to teach you, at least right now. And now I'm going to pull up some examples. Okay, so right here is where you would want to pause. So we have a specific A and B, and then we're going to try to solve for these sets. Okay, so this first one, A union B. Well, how I like to do is I start with the first one. So 1, 2, 3, and now if I go into B, okay, 1, that's already in A, so I don't need to count that again. Okay, the set that has 2 in it, and I have that, I have 3, but I don't have 4. So who does A and B have in common, the intersection? Oh, well, 1 and 3, actually. Oops, forgot to get rid of that. Okay, so A union the empty set. Well, that's just A. A intersect the empty set, so how many elements does the empty set and A have in common? Well, they have none, so that's the empty set. How about A minus B? So that's another way we call the set difference between two sets. So sometimes we say A minus B. So A minus B, well, we're going to take all the elements in A and get rid of any of them that are in B. The important ones I could pay attention to are 1 and 3, right? Because those are ones that are in A and B. So this is the set. So not 1 because 1's in B. 2 is in A, but it's not in B. 3 is in B. Okay. So it's just a set containing 2. Which is funny because it's an element in B. I think I did that on purpose, probably. Okay, so what's A minus the empty set? So what's an element in A that's in the empty set? Or that's not in the empty set? Well, all the elements in A are not in the empty set. So it's just going to be A again. Okay? How about the empty set minus A? Ooh, that's an interesting one. So let's talk about, so I want it to be elements X such that X is in the empty set and X is not in A. What elements look like that? Nothing, because nothing's in the empty set. Okay, so we have the empty set. You can subtract a bigger set from a smaller set. It's just the only elements that you care about is the ones that they have in common. Okay? All right, so this one just is what it is. You could think about that one. A minus A, so all the elements in A that are not in A. The empty set, because there are none. All right, so now we're going to talk about some universal sets. So if the universal set is the integers, and A are the even integers, then a complement, well, who do we have left after we take away all the even integers? We have the odd integers. All right, so what if our universal set looks like this weird thing? Okay, so a complement is just going to be all the elements in our universal set that are not in A. Okay, so I'm just not going to count that one, and I'm going to write every other one. Okay, cool. So now I'm going to lead a small discussion, and I may have already started it, so if you get a bit confused, you can rewind this video to the beginning of the examples. So in general, how else can we write A minus B using our other definitions? Consider two sets A and B, and we want to think about A minus B, how we can represent A minus B with respect to our other definitions that we said. So first, let's start by thinking, do we care about elements in B that are not in A? No, because this set is written as X such that X is in A and X is not in B. So if an element is in B and it's not in A, we don't care. We don't care about any elements that are not in A because that doesn't satisfy our first condition. So what's a way that we can restrict B to only elements that are in B and in A? The intersection. Okay, so this is actually equal to A minus A intersected with B. Not because B equals A intersect B, that is not necessarily true. There might be some cases where it is true, but that's not always true. It's this minus, right? Because I don't care about the other elements in B that are not in A. So the only ones that I care about are the ones that are in A and are in B. Well, what set does that look like? That looks like our intersection. The intersection is the elements that are in both A and B. Okay, let's think about some general Venn diagram. So here our box is our universal set, U. And let's say this is A or something, I don't know. And then let's make B nice. So this is A, this is B. Okay, so if I want A minus B, I want all the elements in here that are not in here. Okay, so who does that leave us with? That leaves us with all this. So the green is what we want. Okay, so this might not be completely like, aha, right away. We need to kind of mess around with some things. So let's look at some different sets, okay? How do we get rid of B stuff? What are some things besides just minusing B? Well, we can take B complement. What does B complement look like? Well, it's all these, it's everything besides B. Okay. So that gets us part of the way there. What do you think we can do with that to get green? Well, we can intersect it with A, because we're not going to get this part over here because blue already doesn't have that part. So it's not going to be in their intersection. So further, we get that this is equal to A intersected with B. Okay, so all three of these sets are equal. How cool is that? We would need some, this is just a sketch of the proof. This isn't like a rigorous proof, but we haven't learned exactly how to do rigorous proofs yet. So right now I'm just doing sketches. So this is an exercise. This is just something for you to do at home. I'm certainly not saying to do all 14. Just do a couple that maybe you're suspicious of, or you're like, I don't really see why that is. Just go through. So this is a proposition. A, B, and C are all subsets, meaning that they're sets of the universal set U. Then all of the following hold. So all of these equivalencies are true, or subset symbols. Yeah, so this is a nice thing. These are really important to know. Soon they should become second nature, but you have to learn them first for them to become second nature.